Check it out now, y'all.
nanoHUB-U, online instruction.
Well, welcome to Lecture 3. In this lecture, we're going to talk about one more transistor. This is a bipolar transistor, or a bipolar junction transistor. And that's what I mean by BJT. Sometimes people think of this as a fundamentally different kind of transistor. You'll hear people say there are two kinds of transistors. There are field effect transistors that are voltage controlled devices. You control it with a gate voltage. And there are bipolar transistors that are current controlled devices. You control it with a base current. Actually, they operate by exactly the same barrier controlling principles. So what I want to do is to talk about this device, and then we will be ready to move on to some circuit considerations for the rest of the week. Okay, so back to my list of transistors, and remember, this is just a partial list. There are many transistors. We could spend the rest of the week and a few more weeks talking about different kinds of transistors. We're just going to do one more of them, actually two. We're going to talk about bipolar junction transistors, but we're going to emphasize heterojunction bipolar transistors, HBTs, and we'll mention what a double heterojunction bipolar transistor is, a DHBT. Okay, so I want to mention, a field effect transistor is just a very easy to understand way to make an electronic device. So this is from a patent application in the 1920s and 30s. Two people, one in England and one in Germany, I believe, patented the concept for a field effect transistor. So here you can see a thin semiconducting film, you can see the source and the drain contacts and a gate. It's just an eminently sensible way to think about making a transistor, and people thought of it a long time ago, but it was very difficult to make. Now this led in the 1940s to a major program at Bell Laboratories. So Bell Laboratories was having trouble in their electronics, their vacuum tube based electronics. The main device for electronics at that time were vacuum tubes. They consumed a lot of power and they burned out frequently. They weren't very reliable. So they sought a solid state replacement for the vacuum tube. And they launched a major program. They were trying to build this device essentially. And what happened is they invented the transistor and received the Nobel Prize for it and really changed the course of history. These are the three people, John Bardeen, William Shockley, and Walter Brattain. They're in the lab looking at one of those transistors. If you take a look at one of those transistors, it's actually, what happened is they weren't able to build the field effect transistor that they tried to build. And in the process of understanding the physics of why they weren't able to build it, they didn't actually invent another transistor. They discovered it by accident. They put wires down on a slab of germanium, and lo and behold, they found an amplification effect. What they built is not what we would call a bipolar junction transistor. We would call it a point contact transistor, but it operated on similar principles, bipolar transport. So that's an example, and it's, if you look at that, it looks like we have a bent paper clip or something here. It would be hard to predict what this would lead to, but it led to modern electronics that we enjoy today. Later on, William Shockley came up with a better structure where you would implement a similar type of device using PN junctions, and that's what we call the BJT, or bipolar junction transistor. So here's a cartoon. It consists of an heavily doped N-type region we call the emitter. This is like the source of a MOSFET. It consists of a P-type material we call the base. This is like the channel of a MOSFET. And then it consists of an N-doped collector and a heavily doped region to make contact to it. That's like the drain region of a MOSFET. Now, there's one difference here that I want to mention. Just like we make metal contact to the source of a MOSFET, we make a metal contact directly to the emitter of a bipolar transistor. We make a metal contact directly to the collector of the bipolar transistor, just as we do directly to the drain of a MOSFET. But what's different is that in a MOSFET, we don't make a contact directly to the P-type channel. We indirectly influence the potential in the P-type channel with a gate voltage. The gate electrode is separated by an insulator. In a bipolar transistor, what's different is we actually make a metal ohmic contact to the p-type region. Okay. Now, the sort of device structure that was used in the 60s and 70s looked like this. This is called a double diffused bipolar junction transistor. The heart of the device is here, the N-type emitter, the P-type base, the N-type collector, but we need to put all of the contacts on the top, so the current has to travel in a 2D and go around the corner and get into the base and into the collector. The structure looked like that. These were really the first successful transistors. The first integrated circuits were all bipolar circuits. For a long time, bipolar transistors were much higher performance and much higher speed than MOSFETs were. The first MOSFETs weren't made until about the 1960s. In the 1970s, MOSFET technology was used for low performance applications, but as MOSFETs got smaller and smaller and their speed got better and better, they slowly took over the applications, and now bipolar transistors are used for certain niche applications, and MOSFETs have taken over most of the applications. So what we want to do in this lecture is to try to understand how these transistors operate. And to do that, I need to review a little bit about semiconductor p-n junctions. And we're just going to not get into it too deeply, but just try to understand some key concepts. So here we have an N-type semiconductor. Here we have a P-type semiconductor. Fermi level by the conduction band in the N-type semiconductor. Fermi level by the valence band in the P-type semiconductor. Those Fermi levels are separated, so when we put them together, the charge will flow from higher Fermi level to the lower Fermi level. Electric fields will get set up. A potential difference will get set up. That will align the bands and bring the Fermi levels equal, and that will lead to a built-in potential. So when we get all done, conceptually we think about putting this N-type layer and P-type layer together. Our equilibrium energy band diagram will look like this. The Fermi level must be constant in equilibrium, near the conduction band on the N side, near the valence band on the P side. And there is a built-in potential between the N and the P region that was set up by this charge movement from one side to the other, and which now maintains equilibrium conditions. Okay. Now, if we apply a forward bias to this p-n junction, what we do with a forward bias is we apply a positive voltage to the P side, or a negative voltage to the N side. It doesn't matter. The ohmic contact, the way we think about an ohmic contact is the ohmic contact on the P side makes a connection to the quasi-Fermi level on the P side. The ohmic contact on the N side makes a connection to the quasi-Fermi level for electrons on the N side. When we apply a positive voltage, we pull that quasi-Fermi level for holes down. In order to maintain charge neutrality, we have to keep the separation between the quasi-Fermi level and the valence band constant. And the Poisson equation makes sure that we do that. So when we're all done, we pull everything on the P side down by the applied forward bias. That reduces the energy barrier. We had an energy barrier of roughly the band gap to begin with. And now that we've applied a positive voltage, we've lowered that by a few tenths of a volt or several tenths of a volt, and now we have a lower energy barrier. That lower energy barrier now means that it's much more probable for electrons to hop over the barrier from the N side to the P side. Remember, their probability of hopping over a barrier is e to the minus barrier height over kT. We've lowered the barrier height, so we've enhanced that probability exponentially. That means that the density of electrons on the P side, right at the top of that barrier, is what it was in equilibrium. That's what I've denoted as NP naught here. That's just Ni squared divided by the doping density on the P side. But it's exponentially enhanced by e to the q forward bias over kT. Then on the other side, we have an ohmic contact. What an ohmic contact does, if it's an ideal one, is any electron that gets there immediately gets sent out the circuit, or immediately recombines at the ohmic contact. So we maintain equilibrium conditions there. So the electron density there is always its equilibrium value, Ni squared over Na, but at the other end of the P region, it's exponentially increased when we forward bias the p-n junction. So that's basically how a PN junction operates. Let's see if we can deduce what the current is when we forward bias a PN junction. So we have this N region, we have this P region, we have this barrier in between where we're depleted of carriers. If we forward bias this PN junction, we inject electrons from the N side to the P side and current flows. Now what happens is we inject electrons to the P side, they diffuse across the P region, and then they recombine at the ohmic contact and one goes out to contact. So the current in the P region consists of minority carrier electrons diffusing across the P region. So that's just Fick's law. So electrons go diffuse down a concentration gradient, but they have a negative sign, so we end up with a positive sign there. We have to deduce the concentration gradient. If the P region is short enough, and good bipolar transistors are always short enough, then the electrons don't have any chance to recombine with a hole while they diffuse across it. The profile is just linear, so the concentration gradient is just the value at the beginning of the P region minus the value at the end of the P region divided by the width of the P region. So we get this expression for the current, and we pull out the common factor, the equilibrium electron density, and we get this expression for the IV characteristic of a PN junction. So that's the classic textbook expression for the forward bias current of a PN junction. Now, when we forward bias the junction, two things happen. That's why this is called a bipolar junction transistor. We lower the barriers for electrons, we get electron flow, but we also lower the barrier for holes, and we get electrons or holes injected in the opposite direction. And you can work through the same argument, and the hole current depends on the hole diffusion coefficient, on the width of the N region, on the equilibrium density of minority carrier holes, but it also goes exponentially with voltage. Okay. All right, so we end up being able to understand the current flow in a PN junction, and that's enough for us to figure out how bipolar junction transistors work. So let's do that. Remember, the first step to understanding a device is to draw an energy band diagram. I didn't do that for the HIMT, because it's the same as it is for a MOSFET. But if we do it for a bipolar transistor, it's relatively easy to do. We have the conduction band by the Fermi level in the emitter. We have the valence band by the Fermi level in the base. And then we have another N-type region. So this is what the equilibrium energy band diagram looks like. Now, if we apply a forward bias, what happens? Well, we take the forward bias. A positive forward bias will lower the energies in the P region and pull that down. If I apply a reverse bias to the collector, that means a positive voltage on the N region. That positive voltage will pull the collector down as well. So the way we operate a bipolar transistor in what's called its active region is we put a forward bias between the base and the emitter, and we put a reverse bias between the collector and the base. And we just pull those energy bands down. If you do that, this is what we get. We've pulled the barrier down in the P region, and we've pulled the bands way down in the N region because we've applied positive voltages on both sides. So the forward bias on the base lowers the barrier between the emitter and the base. What the ohmic contact does is it attaches to the majority carrier quasi-Fermi level in the base, that's F sub P for holes, and pulls it down. If the emitter was grounded, the quasi-Fermi level for electrons stays where it was in equilibrium, and now we've separated them by the base emitter voltage. That lowers the energy barrier, and it means electrons can hop from the emitter. That's why it's called the emitter. The electron is emitting electrons into the base. They diffuse across the base, and then they just flow downhill and go out to contact. That's our collector current, runs around the external circuit, comes back in the emitter to replace the one that we've lost, and that's how steady state current flows. So you'll notice that this is a barrier-controlled device, just like a MOSFET. The only difference is that we have a direct connection to the P region with this base contact, not an indirect region through the gate electrode and insulator as we do in a MOSFET. But the operating principles are the same. We're lowering an energy barrier, which increases current flow. So in this active region of operation, we forward bias the emitter-base junction. we reverse bias the base collector junction. If we forward bias the emitter base junction, we inject electrons from the emitter to the base, and we get the current expression that we derived earlier for a PN junction. The collector current then, there's some cross-sectional area of the emitter coming out of this page. We multiply by that, and we have an expression for the electron current or the collector current, which is just this current that comes back out. I'm writing here for the equilibrium electron density in the base, Ni squared divided by Na. And I'm differentiating, this is Ni squared in the base because I'm injecting electrons into the base. You might wonder why I'm doing that. You know, why do I worry if this is one semiconductor, Ni is the same in the emitter, base, and collector? Well, when we talk about heterojunction bipolars, that won't be the case. So let's keep track of that for now. When we forward bias this junction, we also back inject holes into the emitter. And that current is just like the one for electrons, but it depends on the width of the emitter, not the width of the base. It depends on the hole diffusion coefficient, not the electron diffusion coefficient. It depends on the minority density of holes, not electrons. But it depends on the same forward bias, because that same forward bias is lowering the barrier in both cases. Now, every time we lose a hole from the base, another one has to come in the base electrode and replace it. So this current is our base current. And we can write then the base current with this expression, and the equilibrium hole density is just Ni squared in the emitter divided by the doping in the emitter. So we get those two simple expressions. We're ignoring things like recombination in the base, which if we have a good transistor is not a very important factor. And these are really, they're simple, but they're really very good descriptions of what goes on in a decently operating transistor. So we have these two expressions, collector current, base current. Notice if you divide the two, it's just a number. That's a number we call beta, the ratio of the collector current to the base current. And you can see that the collector current is beta times the base current. This is why people like to call this an current control device. You squirt a base current in, you get beta times that base current out the collector. You know? But it's all happening because we're modulating energy barriers inside. So this is what goes on in the active region. We squirt a base current in, a collector current that's beta times that flows. Beta is a key device parameter for the device designer. It depends on the ratio between the emitter doping to the base doping, depends on a ratio of diffusion coefficient, depends on the ratios of thicknesses of those layers, and depends on the ratio of the intrinsic carrier concentration in the two layers. If both layers are silicon, then that last factor is unity and just drops out. The biggest factor we have to play with is the doping. If we dope the emitter 10 times or 100 times what we dope the base, then our beta is going to be on the order of 10 or 100 times, which is a good high gain transistor. These are what the IV characteristics look like. We can plot the output characteristics. So this is the collector current versus collector voltage. They look like those of a FET. Each of these curves corresponds to a different base current that we could squirt in. We could plot those. These are like the gate voltage steps in a MOSFET, but since the current is going exponentially in a PN junction, you know, we would not have equal base voltage steps. It's easier to plot it in terms of IB because we have equal steps in IB. So this is our active region. Emitter base is forward biased, base collector is reverse biased. In this region, beta is just the ratio of the collector current to the base current. There's a little bit of slope in this region, just like we saw in a MOSFET. That's called the early effect. We could also plot these characteristics as the transfer characteristics. Output current on a log scale versus input voltage at the base emitter terminal. If you do that, what we'll find is that the output current goes exponentially with the base emitter voltage until you get to very high currents where series resistance and some other effects cause it to roll over a little bit. The slope is ideal. It's 60 millivolts per decade. That happens because we have a direct connection to the p-type base, not an indirect connection through this oxide. and it continues to very high current levels. So we get this exponential slope all the way from subthreshold to above threshold, and that's a fundamental difference between a MOSFET and a bipolar transistor. We get that steep dependency all the way above threshold. The base current is a factor of beta times lower than that. Okay, so let's take a look at modern transistors are done a little bit differently, and it's an idea that William Shockley thought of a long time ago and was discussed in the 1950s, but it became to be, the technology to implement it became practical in the 80s really. These are called heterojunction bipolar transistors, and the idea is very simple. The current that we want is the electron current, which then gets injected into the base and comes out the collector. That's proportional to Ni squared in the base. The current that we don't want, that lowers the beta, is the back-injected hole current, and that's proportional to Ni squared in the emitter. Well, the ratio of those two currents gives us beta. If the emitter and base are made out of the same materials, the ratio of Ni squared is 1. But Ni goes as e to the minus band gap over 2 kT. So what if we were to make the emitter out of a material that has a wider band gap than the base? Then Ni squared in the emitter would be exponentially smaller than Ni squared in the base. And this factor at the end could become very large. In fact, if we do a little bit of algebra here, you'll see that the gain would increase as e to the change in band gap divided by kT. So we could get enormously high gains. That's not actually what people use it for. What people do use it for is to dope the base very heavily, which would normally give us a low gain, and then to offset that lower factor here with a band gap difference. That means we can get a moderate gain that we need for circuits, but we can have a very low base resistance, which leads to very good high frequency performance. Now, what's a double HBT? A double HBT is we make the emitter and the base out of different materials. Sometimes the emitter, base, and collector are made of 3 different materials. Sometimes we use the same material for the emitter and collector. If we use the same material, we have symmetrical operation. You know, MOSFET is symmetrical. You know, in a circuit, you can interchange source and drain and everything is the same. If we do a double HBT, we can get symmetrical operation. That's sometimes advantageous. You know, there are other advantages that I won't go into details to, you know, things having to do with reduced charge storage for switching and reduced offset voltages and things like that. A very important advantage is that we can have a high breakdown voltage. If we apply a large voltage to the collector, which we'll need if we're doing power amplification, if we have a wider band gap, then the breakdown voltage of the collector is increased, and that's very advantageous. Okay, so those are the basic operating principles. I just very quickly want to say something about modern HBTs and thank my colleague Mark Rodwell at UC Santa Barbara for helping me put this material together, just to give you a flavor for HBTs today. So here's one example of an indium phosphide InGaAs-based HBT. So if we look at this layers, you know, it consists of several different layers. There's a small band gap layer to make good ohmic contact to the emitter. There is an emitter layer here, which is made out of an indium phosphide layer. There is a base in which is made out of an indium gallium arsenide layer, which is lattice matched or close, and has a smaller band gap. So we have our wide band gap emitter and our smaller band gap base. You'll notice that in this material system, the conduction bands in the wide band gap emitter and in the narrow band gap base don't line up. You know, there's a band offset. That frequently occurs. And then in the collector, we make the collector out of a wider band gap region. And actually, we have to worry about the fact when we increase the band gap that we don't create potential wells that trap electrons and make it hard for them to come out the collector. There's some grading that goes on here to make sure that we gradually increase the band gap and widen it so that electrons can flow across that graded region and get out the collector. Okay, and then the heart of the collector then is a wider band gap indium phosphide layer, which increases the breakdown voltage. The fabrication process, they're getting more sophisticated, but the basic process that was first used goes something like this. You grow this epitaxial layer, deposit your emitter contact and define it, then etch through the emitter to isolate the emitter. Now we can do an additional metal deposition, which will cover that metal again, but will also deposit right on the base, very, very close to the emitter to lower resistance, which is what we want. Then we do another etch to isolate the base, and then we etch down into the heavily doped subcollector where we can make a good ohmic contact. And we do another metal evaporation that self-aligns the contact and makes us a low series resistance in the collector as well. So the processes can be quite simple. The dimensions are quite small. You know, what are the scaling challenges for this technology? Well, it's making these devices are frequently operated at very high current densities to charge big capacitors and operate at high speeds while doing so. So we have very high current densities, and you have to pay a lot of attention to series resistances at the emitter and the base. So that's a key technological challenge. They operate at such high carrier densities, and these 3,5 materials tend to have poorer thermal conductivity than silicon, that the heating of the device is a problem also. And the collector design, such that we don't trap carriers in potential wells and we get sufficient breakdown voltages, is also an issue too, as well as the yield of these circuits. So these are some typical results, and we're going to talk a little bit more about this when we talk later on about circuits. But what you'll see here are IV characteristics for a couple of different devices for a couple of different dimensions. You can see that these devices can have very heavily doped bases, which lead to very low output conductances or high output resistances, which is very beneficial. You'll also see these curves turning around and dropping. That's a signature of self-heating. At higher current densities, the device is actually heating up and the device performance is degrading. These are plots of the frequency performance, and we will discuss this in the last lecture. You're seeing a couple of different plots of the common emitter current gain and the maximum frequency of oscillation or power gain. When the gain drops to 0 decibels, remember decibel is a logarithm, so 0 dB means the gain is dropped to 1. You can't make that's as high a frequency as you can make a useful amplifying circuit. When the gain is less than 1, you don't have anything useful. So that's a figure of merit, and you can see those figures of merits up there in hundreds of gigahertz and approaching terahertz. So these are really high frequency devices that operate at these two key figures of merit that we will discuss very briefly in the last lecture this week. And they're up there in this near terahertz regime. Now, to wrap up, I just want to return to MOSFETs. So remember when I drew this energy band diagram for the MOSFET, I sort of made an analogy to a bipolar transistor. As I said, you know, it's widely thought that bipolar transistors and MOSFETs are two different transistors fundamentally, but they're really not. Their energy band diagrams look very similar. In a MOSFET, we have this bottleneck near the beginning of the channel that carriers have to diffuse across. In a bipolar transistor, that's just the base that the carriers have to diffuse across. So we have something that looks like a base in both cases. In a MOSFET, we have a high field region in the channel near the drain that collects those carriers that diffuse across. In a bipolar transistor, we call that the collector. They're really the same device. So to wrap up, 3.5 HBTs are an important technology for high frequency applications. They offer speeds that are very close to HEMPs. You know, these numbers are close to the ones that we quoted for HEMPs, you know, above terahertz F maxes. If you compare them to HEMPs, they deliver higher powers. It's actually easier to get higher integration densities with them. So they're used in power amplification and some other applications. You might have a HEMP in your cell phone. You'll have HBTs in the cell phone towers, for example. But the important point for us is that HBTs operate in this same barrier-controlled mode that silicon MOSFETs do. So it's a different type of transistor, but one whose essential physics is very similar. Okay, so we've had a look at a couple of different types of transistors in addition to the silicon MOSFET that we spent most of our time talking about. The next topic that we're going to discuss for the remainder of this week is circuits. All of these devices are useful because they provide us with useful circuit capabilities. So for the next three lectures, we'll try to discuss some circuit fundamentals that apply to both MOSFETs and bipolars.